Okay, some discussion with my daughter to balik kampung. Okay, so this one to one, this one from where? Okay, no. Oh, I already okay. Open up this. Okay, now yeah, I must remember to record Record mana dia? Okay, double check, okay, whether I'm recording, okay, whereby you can see on your side, All right, okay, in this part here, what we are going to study on this first topic here is called HDL, Hardware Description Language. So in this HDL here, so let me turn on first, okay. In this HDL languages here, before we actually go and study what is this one here, we go for a little bit of why we need to study, what is the advantage, a little bit of history about this HDL. After all, okay, people okay put in so much effort, so we appreciate, okay, and recognize their effort. So HDL is a software solutions. Why we need to study is because, okay, digital system is getting, okay, very, very complex. Okay, so for a complex systems here, if you are doing designing and you want to get it right at the first time, first design, everything perfect, chances is getting lower and lower lah. All right, so therefore we need a software. We create, okay, or put our thinking, everything into the design, and we confirm that it is working first before we transfer them into the hardware. So with this, okay, you are going to find that chances of getting, okay, correct in the first time in the hardware, okay, much, much higher now. Therefore, in this case here, you cut costs, save money, and save time. Money, okay, is related to your investment. So if you can cut costs, that is to say that, okay, money that you are going to invest in designing this hardware here will be lesser. So these are increasing of design complexity, increasing of cost and time investment, and also complexity knowledge, okay, required to related to your list of complexity here. You find that all this part here push, okay, the trend to make use of software to do the design first. Okay, so of course you may ask, okay, why must use HDL? Why must use VHDL? Can I use other languages? Answer is yes, but HDL or VHDL here is one of the most popular languages. Okay, so therefore, because it's one of the most popular, so you find that it is more mature. So a lot of support. All right, a lot of support to solve, okay, whatever related problems. So they are mature enough, okay, to cater for all the possibility. So other languages, okay, may be inadequate, okay, inadequate of other existing languages. Answer here tells you that you can use other language, but may not be as good as VHDL. Okay. Now, these are VHDL that we are going to use here. You are going to find that there are some vendors. That means a supplier supplies the hardware. This hardware can take your VHDL. So the program that we are writing here, we actually no need to bother, okay, eventually what hardware you are going to use. We just write our software based on VHDL. Then subsequently, when we want to do or downloading into our hardware at that time, we need to do some hardware setting. So in this case here, it is good. It then become, okay, vendor independent. It don't depends on your vendor anymore. Whichever is a supplier, you can use it. Okay, so it's free of this vendor dependency. Okay, like a very popular example here is Altera. That is what we are going to use in the lab lah. Another one is Xylene. Okay, these are the two very popular ones. So I don't care you are using, okay, Altera or using this Xylene, both, no problems. If I write my code, I can download to Xylene board. I can download to Altera board, which is our DE2 board. So it is vendor, okay, independency. So don't care about the supplier, okay. Now, of course, okay, different vendor, we have different, setting. So we have to do some setting before we can use it. So you might need to have do some document exchange because of the setting problems. Okay, so you want to download into Altera, follow this setting. Want to download to Xylene board, different setting. So with all these things here, you find that, oh, not bad, VHDL. We can use VHDL to model what we want. Then when come to download the time, we only do the slide setting here. So this is the reason why we want to study HDL language. And the type of HDL language that we are going to go for is the VHDL. Okay, a little bit of history on this VHDL. Now, they started to talk about this VHDL here is in 1981. Now it's 2022. Okay, 2022. So after about 40 years, so you find that, okay, things are getting very matured already. So over here, they start, okay, to do all these requests, okay, start to set up some standard. Of course, everything when they start at time, okay, there's no standard at all. So once, okay, no standard, everybody will come out there with their own standard. Therefore, okay, this institution, IEEE, Institute of Electrical Electronics Engineering comes in. They are the institution set the standard. So once they set the standard, everybody follow and makes, okay, the learning process getting easier. So they set up the standard in 1987. Subsequently, they revised the standard 1993. All right. So still not enough. Revise the standard again, and so on until it then become very matured and not much, okay, changes need to be done already. So after about 40 years of effort, so you find that VHDL now is very mature. That when we use it, okay, it is a kind of like a high level, okay, high level language. High level means that it's like English-like language, whereby you look at it, sometimes you agak, you know, okay, what is this one here, what is that one that, okay, if you already have some basic knowledge. Okay, so this is the history about your VHDL. Now, in this history of this type of VHDL here, okay, when we are doing any programming that time, okay, we must really make sure that, okay, the type of programs, okay, or the type of language that we are learning here, okay, must be readable, easy to read. You must document it properly, so it is document based. Okay, so must make sure that, okay, everybody, other people, okay, who are not writing the program, okay, will be able to read your program, will be able to also predict agak-agak know, okay, your program, and based on the simulation that you submit, okay, they know, oh, this program that you are written here is trying to model, say, for example, a multiplexer. So these are the things that is being required in any of the programming. All right. So advantages of having your VHDL here, you find that, okay, there are some standard format for us to follow. And this with this standard format here, you find that, okay, you can actually reuse the design. So the design can be exchanged. You can reuse the design. You change your hardware, my program remain unchanged. Okay, program never change. Technology change, but program remain the same. Different vendor that I mentioned just now. Your design here can be very simple or very big. Normally, we will start the design, okay, with a very simple, we call it as a simple entity first. Then after, okay, this entity, okay, we can interconnect them, means that make it become larger. But good thing about this one here is that when I am doing my testing that time, I test small part. I make sure all the small part here working properly first. Then only I join them. So when come to final simulation that time, then you're going to find that because all the small parts are working, final simulation most probably are going to working because there is no error in the individual parts already. So you're going to find that with that, okay, they can support larger components. Actually come from all the small design. So you can have different type of modeling. The two different type of modeling, okay, that we are going to study later here is one is called behavioral. Okay, the other one is called structural. Behavioral here is if we know, okay, how the component work, we just write it like describe how it work. Then if you were to ask me, hey, what component are you using, component or what gates are you using for this design? My answer is I don't know. I only know how it works. So I describe the software in behavioral. You are going to see later. Second one, structural. Structural here basically is like using, okay, component, you connect them, you build a circuit in a structural model, build a circuit. So this one, if you ask me what component that I'm using, yeah, I can answer. This one, I cannot answer. But both of them, okay, can be used, okay, to describe the same component or to program a same component, depending, okay, which one you think is easier. So they can have a wide range of expressions in modeling, not restrict to one. Okay, in a system, you can actually mix them also. Some are behavioral, some are structural. So combine them are still working. All right. So after, okay, join all these, okay, simulation is very important. So it's simulation oriented. So you can use, okay, the model sim available in the package that I asked you all to download, so-called Quarters, Quarters 2. All right, or write your own test bed. Usually, okay, if the design, okay, is very compact, very big, okay, so you write your test bed. But for VR, okay, as a beginner to learn, okay, you will mainly use the simulation packages provided. That is the Simulink. All right. Model sim. I talked about this part already. Okay, model sim is a type of a simulation software for us to do simulation. Okay, so on top of the advantages here, you are going to find that, okay, we can define some our own value. Okay, so in the software itself, we can have user-defined packages. Later on, there's an example on this traffic light. If you want to model a traffic light, how you're going to do it, you can do user-defined values. All right, so you are going to find that, okay, they are very fast, okay, they can go up to us like a picosecond, nanosecond, these are things. So it's a timing construct. All right, they can really model, okay, the hardware, okay, based on the timing that you want. All right, so these are the advantages and drive us to study VHDL. Of course, okay, nothing is perfect. You also have some drawback. So as your design getting or your programs, your this design getting more complex, so you find that complex too may be required because you want to test them thoroughly. Okay, cannot afford to have any mistake. Okay, so you need to test them thoroughly. You may need to write your own test bands to test whatever, okay, possible mistake in the programs. Then because of complex tools here, you find that this style of design here maybe come to simulations maybe slow because they test all the possibility. But this drawback here compared to the advantages here, you find that okay, maybe it's not so significant. So you have more advantages as compared to more drawback. So therefore, you still need to study this one. Okay. Now, in this VHDL here, these are the main features here. Like I mentioned just now, okay, we have behavioral model. All right, we have a structural model. All right, so these are the model here. So in the beginning, okay, we may need to have some data flow, whether the signal, okay, is coming in as input or going out as output. Everything we have to define. So the data flow comes here. And subsequently, okay, the timing here is more on your simulation. So these are the main thing. All right. So in one component, okay, if you design a simple component here, you either use this one or, okay, either this one for small design. Okay, design. But for larger design, okay, we can have both. Okay, both are behavioral and structural. Simple, no need, just choose one. Okay, larger one, no, we go for both. Okay, so these are sort of like some basic, okay, introductions here, and you are going to find that, okay, in behavioral design here, we only describe how it works. Then you ask me what type of gates that they are using, like I talked just now. What type of gate are they using? I'm going to tell you I don't know. I only know how it works. Because based on the descriptions, I only know how it works. Whereas for structural, I know how it is being connected using the types of component. So I know what gate they are using, what multiplexer, what decoder, maybe what flip-flop that I'm using, okay, under the structural model. So from here, you know that structural model in this case here is related to the gate. Behavioral here related to just algorithm. Okay, finite state machine. I only tell you the register transfer language. So this signal go to that signal, how they go, what component they are using, never mind. The system can cater by itself. Okay, so that is the beauty of this. The system can cater for themselves what component they are going to use under the behavioral model. So your job here is only focused on writing the program to describe how it works in behavioral model. In structural model, you describe the connections of all the gates, all components. So if you connect wrongly, answer wrong. All right, so connection very important. So we will study both. Okay, we will study both. All right. Okay, so layout here can be okay part of and parcel of your structural. Okay, so you can be able to sort of okay list out okay the interconnections of all. But in more detailed part, it is based on the gates. Once the gate okay you interconnect them already, it forms the layout that you want. Okay, so we say that VHDL here is a data flow language. Now compare C. You have learned C. Compare C with VHDL here. In the C, okay, you say that X is equals to A and B. So here it's trying to tell you here, oh, my X value here is equals to my A and with my B only. Every time this thing happen. Okay, every time think this, you write this as segments here, then your X is the same as your A and B. Whereas in VHDL here, you are going to find that they are going to set up a permanent link. Okay, this is every time. So this one here is when I set up this link here, my X is like that already. So my X in this case here is okay, this is a N. This N here is not English N. So this is a logic AND gate. Okay, this is a logic AND gate. Meaning is like this. I got A input, I got B output, I AND them together, it forms my Y. So this part here, you actually describe this way. So a permanent link is created between your A, B, and your X. This one. Okay, so my X here will change because this is an AND gate. I hope you still remember. AND gate, my A and B input, X. So every time my logic for A and B here changing, it will cause my output here, X here to change. So this one will be 0, 0, 0, 1. So if initially you put a 0, 1 to A and B, logic 0, 1 and B to A, you got a 0. But the moment your B, you change it to, both A and B, you change it to 1, 1, then immediately you are going to find that your X here will change immediately to logic 1. So permanent link. So fixed already. Okay, that this part here. And you find that therefore, with this permanent link here, you cannot say that, oh, X same as A and B. Then later on, X same as C and D. Answer is cannot do this way. So this one, if you want, change lah to Y. Okay, so these are two different gates already. This is an AND gate, another AND gate. So their output, you label it differently. Whereas in C, they can. Okay, so don't have your this C language mentality, okay, being applied to your this VHDL here. Okay, so permanent fix already. So if I want to make it work, I must use different variable. All right. Okay, so this is a general knowledge, okay, that we know about this VHDL compared to other types of programming language here. Then now we look at entity. Now, before I go into detail of this entity here, now you are going to find that, okay, in a digital component, when you do your this you all never go to lab before, okay, you if you see those are IC, so let's say this is the IC. All right, simple IC, you have some pin, right? Okay, outside here also you have some pin, right? So when I look at this IC here, wow, where got 3-pin IC one? Okay, 4-pin. Okay, 4-pin IC. So when I see this IC here, I know, oh, this cover here is black color. Oh, this IC here, the cover here is black color. Okay, then this pin here. What is this thing here for? Is it input, output, and so on, power pin and that? Okay, what is all this? So these are the part, okay, that I see visible. I can see there are 4 pins here. If here got 4, the other side also got another 4. All right, then this IC here, definitely they have a name. Let's say, for example, I simply put one name that we know 741, the OM. Okay, this IC 741. So this is the name for this IC. These are the so-called interface to communicate to other components or to our circuit design. So in VHDL, entity means that this one. This whole thing is what we call entity. They don't use it. They don't call it component. They call it as entity. This is an entity. Okay, this entity. Now, in this entity here, there are visible parts. Means something that you can see. 1, 2, 3, 4. This 4-pin, another 4-pin. All right, so these are the visible part whereby I need to describe. Okay, so this entity here first. So you find that, okay, in this entity here, I need to tell you which pin, okay, okay, what function they are carried out, and the name of the entity. So when I start writing program, I start with the word here, entity, the name, for example, so example LS741, just example only. So this is a name for this entity is, then I am going to describe to you the pin. Okay, what are the pin that you are going to use here? Then I need to close this entity with the entity name, the LS741. All right, so very difficult to remember. Never mind. We will look at an example, and bear in mind that this is what you can see, visible. The hardware itself, you can see. So let's say a simple example here is a multiplexer 2-to-1. So in my multiplexers here, of course, the name here, I must give it a name. So in this name here, we call marks 2. Some of the students will ask me, why don't you call it 2 marks? 2 input ma. 2 mark. Why call marks 2? Why you never say, okay, multiplexers output 2 marks 1? Answer is, do we need to tell the output? All multiplexer got 1 output only. So answer is no need to tell lah. Okay, this one no need to tell. Understood, 1 output only. But in VHDL, you cannot have number or digit in front. No, it must be an alphabet. Okay, alphabet. Therefore, to be able to know how many input of this multiplexer, we'll put it at behind here. Marks 2 or 2 inputs. Okay, and output no need to describe, definitely 1 output only. So in this simple multiplexer here, I got 2 input, A input, B input. The name here, you label it suka hati, up to you. And you also know that, okay, multiplexer got a selector. Okay, this selector will decide whether the output will follow A input or B input. Your output here is Y out. You write as Y out. If you don't like the name, like I say Sukahati, you can label it differently. So if this is the component that I want to describe in VHDL, what I'm going to do is I start to describe as this is an entity. Then student ask me, must I start with capital E? Never mind. VHDL, capital, small letter, to them means the same thing. Okay, you can write big E, small e, whole thing, capital letter, no problems. Okay, so they are not case sensitive. So with this, okay, entity marks 2. Name of this entity marks 2 is input, A input, B input, C input, input. So dot, colon, is an input. This one here tells you the input. So port mode. They can only accept input. And what are input they are accepting? Standard logic. STD underscore logic. Then you have a semicolon. To say that, okay, I finished describing this line already. All right. Then you continue. One more pin you haven't described. That is your Y out. You colon again. Say that my out here is a output data only. So you put the word here, out. It's a port mode. You put out. Out standard logic. Okay. What type of information they are going to output? Also the type here will be standard logic. Then here open, here close. After close this bracket, then only semicolon. To indicate that I finish, okay, describing my port. So what is this port here? Basically is your input port, output port. So this port here, inside here tells you the input port and output port. Finish describing, close the bracket, semicolon, then only you end the entity name. So this part here is visible. You see from here, you know that, this multiplexer 2 here, the marks 2, marks 2 here, 1, 2, 3, 3 inputs, 1 output. Okay, how do you know that these are input? Here in, no? How do you know that this is output? Here out, no? What information that they are going to accept for input and output here? Standard logic. So we will come to standard logic later. Okay, so you describe the visible part of your component, or in this case here, we call it entity under these parts. All right, next, another example, a full adder. Now, my full adder here usually will be A, B, then C carry, carry in. I hope you still remember. Let's say you have A, you add up with B. All right. If I just add like that, okay, let's say this is a 0, 0, no problem. I got a 0. But when I have a 1, 1, A is a 1, B is a 1, you add up, you have a 0, 1, isn't it? Okay, this part add up becomes 0, 1. Okay, so this is the what we call as a sum S. Okay, wow. This one here if you do adding, carry out. Okay, this is the carry out. This is adding 2 bit. But when we do design for full adder that time, we may do it as like a continuation, okay? So let's say my A, this is my A and B. My A having 2-bit number, my B is also 2-bit number. So I want to add these two A and B together. So how do you do adding? So if I have a full adder, what I can do here, I add in a C in. Initially, for the, hope you still remember what I cover this one. This is what we call LSB, right? This is what we call MSB. In my LSB here, if I have a carry in, automatically I can add in a 0. No carry in the LSB bit. Okay, so you add up. Okay, so like I told you just now, you add up, you are going to get here 0. Then 1, I cannot write here. This one will come to here. So the carry in for the MSB bit now is a 1. Come from where? From the previous bit. In this line here, you call it carry in. But when come to here, if you are talking this one alone, you are going to call this one here as your carry out. Depends on where you look at it. Carry out, see out, okay? So come to here, become carry in. So maybe I should draw it this way. Now if I'm using 2-bit, so this is the S, this is the C out 0, this is the C in 1. Okay, so A 0, B 0, C in 0. So this bit here, everything I label it as 0. Okay, look at here, C out 0, come to here, become C in 1. Then you have your A1, you have your B1 here. And their output now, S1, C out 1. So if I were to draw it, label it at this way, this will be all my 0. A0, B0, C in 0. So their output, this is a S0, come to here, connected. Okay, connected. So you find that C out 0 becomes your C in 1. Okay, then you go and add up. So you get this one 1. Okay, 1, 0, 0. So your C out 1 is a 1 now. If you have one more bit, C out 1 will then same as your C in 2. Depends on how many bits you want to add up. So that is the concept of your full adder. They cater your carry in. If it's half adder, no carry in. Okay, no carry in, half adder. We study this one in year 1. Okay, so half adder, no carry in. Full adder got carry in. Full adder is more useful. So you find that you can just link them together. Okay, so with this, okay, let's say now I want to design this full adder here. So how am I going to write in HDL? So I start off with writing entity. The name, I call it full adder. Then student ask me, why must have an underscore here? Cannot have full and adder? Answer is no. One word only. One word only. So therefore, I try to join this full and the adder together. Become full adder underscore become one word. All right, so that I can read and understand. You mix everything together, very difficult to understand. So can be quite a long name. Okay, so full adder is how many input and output? So I describe the port. So port, open bracket, 1, 2, 3, 3 input. Now I use a different types of port type. Use the word here, bit. Bit here will show you answer here is either a 0 or 1. Standard logic is more complex. Okay, so bit 0 or 1. Okay, and their output S and carry out here also out, then also bit. Then student ask, okay, can here be bit, here be standard logic? Answer, no, same type. Okay, same type. So if you use bit here, you also use bit. So in most of the case here, you will use a standard logic because it's more realistic to our actual hardware world. Okay, standard logic. But I need to tell you that there are various different types of port touch. Okay, now after this part here, I close the bracket. Okay, close the bracket, semicolon, to indicate that I finished describing my port. Then I end my full adder, semicolon. Okay, and in this part here, you also see that, okay, let me erase this one so that you can see clearer. So in this part here, you also see that, how come some of the word in black color, some of the word in blue color? So you are going to find that this one here are reserved word. Reserved word in the sense that it have a special meaning in VHDL. So you cannot simply use it. Okay, you cannot simply use it. In fact, okay, if you type in the AND, they will change color already. Okay, you will see this one when you're doing your practical. Okay, change color. This N is a logic N, not your English N. All right, so these are all the research work in the sense that, okay, when you type, they have a special meaning in VHDL. And in the quarters 2, that in the software that we are going to learn, they have a color. Okay, if I'm not mistaken, red color. All right. So here we describe the visible part. Then if you ask me how full adder work inside, sorry, we haven't learned that one yet. Okay, so entity here only tell you the visible part, only describe to you the port. Okay, the port, input and output port. Okay, what is the purpose of having your port here? They are going to provide communications with other components because it's like the pin, output pin, input pin. Then you can join your this output pin, okay, to another component of their input pin. All right. So they provide communications with other components. So besides using the word communications here, we can also say they provide the interface because in this computer, okay, when come to this type of things, they always use the word interface. They provide interface with other components. Okay, these port here, you must have their signal name. That is to say, the pin must have a name. Then you must tell them that, okay, they are in input or output. Okay, common one, common input and output. Then you must have a type. So far we have seen here is the bit, here is the standard logic. So far these are the two types that we have seen. So port must have name, mode, and type. What are the port mode available? I already told you the common one, input, output. But there are some, okay, signal here are bidirectional. They can be input, they can be output. So if that is the case here in VHDL, you have to use the word in, out. No spacing, in, out to indicate, okay, they are bidirectional. But when come to using this bidirectional, when you want to do simulation, it's very difficult. So later on, okay, you find out, okay, we try not to use in, out. You will introduce something called signal. Okay, signal to cater for this out or in out or modify, okay, the in out operations here, making use of signal so that when come to simulation, it is easier. All right, of course, if you don't want, you are expert already, okay lah, go for in out. But for us, okay, new, we make sure, okay, try not to use in out. Okay, next is a buffer, okay. The data only used internally. Okay, it's a buffer. Data only used internally, never go out. Okay, into the entity to other components or other entities. Okay, so these are the common one. Okay, after looking at this entity here, I hope you all know that, okay, this entity here are described the visible ports. Okay, visible ports. That is the entity. Like I say, okay, after this, if I only learn this entity, if you were to ask me how it works, I'm going to tell you I don't know. All right, I don't know. So to know how it works, I need architecture. Okay, this architecture. So in this architecture here, we are actually doing the internal aspect of the design. Yeah. Okay, internal aspect of the design. So describe the how this entity here work. Okay, I repeat, describe how entity here work. So this internal aspect here can be in behavioral or structural. Behavioral describe how it work. Structural make use of maybe gates. You interconnect all the gates together to tell interconnect all the gates together, okay, to form a circuit. Okay, the circuit will actually solid features, okay, the functionality of this architecture. So in any of the entity, you have either simple one, simple one, okay, you have a behavioral or structural only, simple one. But if it's a complex one, you can have multiple. Okay, mix lah, behavioral mixed with structural. All right, you can have two. Okay, so single entity can have multiple architecture. This single entity here can be a complex design already. So only complex design, okay, normally, okay, we will mix, okay, making use of behavioral as well as structural. Simple design only, okay, keep to one only. So next, okay, this is a syntax of having your architecture, how you're going to write your architecture here. For all the architecture here, you also give it a name. Oh, usually the name here, okay, we will either put it as a behavioral or structural. Don't think too much, okay? So of the earlier entity name, let's say the Marks II, the full adder. Okay, so this architecture is for Marks II only or for multiplexers only, or sorry, for the full adders only. Okay, so so you have to declare the parts. Okay, then you have to begin how it work, describe how it work. Then you end this architecture with the name that you put here. So these two must have the same name. Okay. Okay, so now if you do not know how D flip-flop here work, doesn't matter. Just get a little bit of knowledge first, okay? What is a behavioral, what is a structural, okay? So don't worry too much, okay, how this thing here work. Get an idea first. Let's say we talk about a D flip-flop. Okay, a D flip-flop be asynchronous, low reset, and positive H clock. So let's say in this case, if I were to draw out the visible part of this, what I understand for this one here, reset. Okay, reset is a low. Low, normally we put a small bubble. Okay, so this is a reset. Okay, low. I put a bubble here. Then positive H clock. H clock. So clock H. So this is the clock, CLK in short. Right? Because this is a D flip-flop, definitely you have a input called D. All right? And you know lah, all flip-flop, right, must have an output called Q, another output called Q bar. This is standard, no need to tell. Must have two outputs. Okay, so this is my D flip-flop. So from here, I see this. I can imagine that the simplest, okay, D flip-flop that I'm dealing with now is like this. Okay, so this one here, if I want to write the entity, I have to say that this is input, this is input, this is input. These two are the output. Then the name I describe. Okay, give it a name. But now, okay, I'm trying to introduce to you how inside here work. There are two ways of doing it, behavioral as well as structural. So we look at behavioral first. So, when we are dealing with flip-flop in real component is every time my clock comes, my clock is like that. Okay, my clock is like that. Every time my clock comes, my flip-flop will work for one time. And depending on the type of clock that they respond to, in this case here is positive edge. That is to say that when rising edge, okay, when this one come, when this thing come to here, D flip-flop work one time. Another clock comes in, rising edge, flip-flop work for another time. And at the same time, if suddenly, okay, I go and put in some signal, a low signal to it. Okay, from high initially, I make a low signal, this low to it. Then you find that this D flip-flop also going to work. They respond to this low signal. My Q is always at logic low. Reset the Q. Reset the Q. So you see now your D flip-flop here responds to reset, responds to clock. Every time reset change or clock change, I need to respond once. Okay, I need to respond once. So with this, okay, I must make sure that every time it work, it's not okay, work for one time, then not working already. No, it must work every time. That is how in VHDL process comes in. This process, okay, sensitive to clock, the CLK, and your reset. Clock, reset means that process is sensitive to clock and reset. What does it mean by this sensitive? Whether the clock change or the reset change, I must run all these things one time. I repeat, when either, okay, your clock here change or your reset change, I need to run this process one time. Okay, I need to run it for one time. If no changes happens at these two, let's say clock spoil already, okay, reset forever at logic 1, then you find that, okay, they won't, no need to work. They can sleep, no need to work. Okay, that is the purpose of process sensitivity list. All flip-flops, if you want them to work, okay, response to clock, reset, or even preset, you must put your whatever that they are sensitive to, okay, into this list here. It can have more than one, okay, 3 or 4. Okay, then process begin. If why I start off with reset first? Because they say asynchronous low reset. That means that, okay, this reset here is of higher priority as compared to my clock. So if my reset is a 0, then my Q will be forever 0. Okay. If you want to talk about logic, you always, okay, have this open okay, inverted comma, close inverted comma, indicating that this is a logic, not the number 0 is a logic 0. If reset is a logic 0, then my output is also a logic 0, reset to 0. So this output here, we use this type of assignment. Output is assigned to logic 0, or 0 is assigned to output. You assign. So this is an assignment. Whereas reset is you compare, test. Reset, is it a 0? Yes, then I do this. If my reset is a 1, then I jump into the else if. This else if is the same as else if. But in VHDL, they cut short. E no more, and the space no more, become else if instead of L is, but meaning exactly the same as L if. Okay? This whole thing is one shot together one. Okay? Clock, apostrophe, event, and clock equals logic 1. This one here, this whole thing, describe to you rising age. Clock event, this is an event. End at logic 1. This is the logic 1. This is the event. Clock event end at logic 1. So try to tell you that this is a rising age. Okay? Then you say that your data, whatever is the input data here, okay, will be assigned to the queue. Okay? No more thing already. I end my if. I must end my process. Okay? After end, remember semicolon, semicolon. Okay, so get this idea here first. So from here now, I know that, oh, this is how this D flip-flop here work. Okay, how it work. When reset is a 0, my Q is a 0. When my reset is a 1, I check my clock. If my clock comes, whatever is a D will become the Q output. So I know how it works under the behavioral model. Okay? But in structural model, you'll find that they will use connections. The D is connected to data, clear is connected to reset, CLK connected to CLK, Q connect to out. So this part here, okay, if we were to sort of go and look at it in detail, you should have your entity declaration first. So just get in mind first, okay, in structural model, we tell the structure, tell the circuit connection. Okay, tell the circuit connections. So they are telling you the circuit connections. Now, with this one here, you may find it a little bit blur, okay? But when come to this tutorial, I got a full questions on this, okay? Then you will find it easier to understand. So here, structural tell you the circuit connection. Here, tell you how it works. If you look at the circuit connection, maybe you do not know how it works. All right. So here you know, but here you ask me what component am I using? I don't know. Here you ask me what component am I using? Yes, I can tell you one by one. But how it works, I don't know. All right. So both of them, okay, have their own how do I say own beauty lah by itself. Okay. But of course, when you are writing the program, you know how it works. Okay, you will know how it works. So up to you, which one you think is more easy. All right. Okay, so we look at another example. This one here, because we have multiplexer, so making use as entity already, maybe it's easier to understand. So in this 2-to-1 multiplexer here, you find that I have now first one, behavioral. I'm going to tell you, okay, my architecture, the name for this architecture, label it as 1. Later I got a 2 Like I say suka hati, okay? Don't think too much. Okay? 1. Of marks 2 is begin. Here I only tell you the connect the how do I say, okay, the flow of it. Okay, the behavior of it. Okay, your Y out here is assigned as A in and with not sim. Sim in is a selector, or you see, when you have a bracket here, you must do first, then only you or you only with B in, B input and your C S C selector input. Then you end 1. So this is the behavior of your multiplexer 2. Do I know the connection? Actually, I don't really know. But if I really want to do this part here, maybe I can. All right. So what you can think of is my A in and not SIM. Okay. Okay, so my A in and not SIM. Wait, let me get the pen first. So in this case here, if I were to look at this one here, you are going to find that, okay, my AND gate, this N means it's an AND gate, is connected to A in and with my not SIM. Yeah. Okay, so this is a SIM, okay, as input lah. Okay, I do this one already. Then next, this one here is your B input and with your S input. Okay, both of them already. So that's why I said must do this one first, then do another this one here first. Then only I all them. Okay, now all them, the output is called Y out. So here describe to you, okay, how it behave. Why, how the signal come in here like that, okay? Take it as behavioral. Okay, whereas the second one, the second model, structural model here, they already have a multiplexer. Okay, now the name of this multiplexer here, they call out this component, Max2. Now, originally this component here got a A, I write inside, got a B, got a S, okay, and got a output called Y. So whatever inside this component, I write it here. All right, so you got this component, then they instantiate these components, they pop map it, pop mapping. That means this port go to where and so on. So they call it as port mapping. So this A, now I'm going to connect to A in. B, I'm going to connect to B in. S, I'm going to connect to S in. Y, connect to Y out. And in these parts here, you are going to find that it's like that. This is a new component that you are forming, okay, with this name. And this new component here is using, okay, the old design of your Max2. You tell the connections here. You tell the connection. My A is connected to A in, B is connected to B in, S is connected to S in, and so on in this design here. So the connection I know exactly based on whatever I described over here. So this is what we call port mapping. Of course, okay, this one here, not much meaning because I'm only using a single components. But if I'm using more components, then you find that more port mapping line I need to write, then you can build a more bigger circuit. Okay, and I repeat here, Max2 is components that I already designed earlier. I reuse it. I call it out to reuse it. How to call out the old entity that I already designed? Use this word here, component. When you see this word component, means that you are using the old entity, okay, for this new design. So you call out this component. This part here, you copy the visible part. Don't go and type instead of ABS, you go and type ASB. No, follow exactly. So normally we copy and paste. All right, copy and paste. Then once, okay, I finish this one, I end this component saying that, oh, I already called out this component. Okay, I must have already called out this component. Then I need to tell the connections of this component that I want to use it for. All right. Any questions? This part here, well, I think can finish this one. Okay, so another example, full adder, which we have the entity one, okay. So you find that now make a more complex, okay, or more complete design here. My this full adder, we start off with this. I think I already described to you all here. Entity full adder is, I got 3 inputs, 2 outputs. Okay, finish this part. After this, I have my architecture. Suka hati, now I want to use the word data flow. So the name for this architecture here is called data flow of full adder is. Then I use a wire. In this case here, wire in VHDL is a signal. And this wire must have a name called X. Wire must also have a type. Same. So if here use bit, here also use bit. Okay? If not, they confuse, cannot map. All right, then I begin. Inside here tells you how this architecture or how this entity of full adder works. Okay, how it works because I'm using the behavioral model. Okay, so over here, let's just work out this. Here, I tell you here, my X here will be assigned with A, XOR B. Still remember your A, XOR, your XOR gate or not? XOR. Look something like this. Okay. My A, XOR B. Output is a wire. I try to differentiate this one. Put it like that. So this is my X, indicating that this is a wire or signal in VHDL. So X is assigned as A XOR B. Next. Okay. My S here is A XOR C in. S. So this is a straight line. Why? Because this is not a signal. This is the D in. And why they say after 10 nanosecond? Because you need to get the result, okay, from these reactions of this XOR gate. So my X result here will only be stabilized. In this example here, prediction is after 10 nanosecond. So signal stable already. All right. Then only they are going to XOR with C to get your S. Okay, this is my S. One of the output. And next, we look at C out. C out here is A and with B. And okay, they never say anything, so I just do it as A and with B. Let's put more obvious. A and with B. All right. Next is X and with C in. X is here. Okay, so I draw this one here first. After this, okay, now I have done this one and I have done this one. Okay, both their outputs here, I all them together because here all. And this one here forms my C out. So which indirectly I'm trying to tell you, this full adder, okay, this full adder, two output, S, the sum, and the carry out, three input, A, B, C in. How they work? Actually, if I draw all these things here didn't tell me the connection. I am the one who come up with the connection. Here only tell me how they behave. So this is still classed under the behavioral model, but I further go and analyze it, okay, to convert them into structural model. Okay, they tell me, oh, this one connect to that one here, that one, they tell me how it behave only. Okay, and what type of component you're using? This one here are the very standard components. Okay, you just it's available in the VHDL or in the quarters 2 that we are going to use later. All right, so with that, okay, now inside of this full adder is like this. Okay, outside entity 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. The outside part, visible part, architecture is this one. All right, so this is the behavioral model. If we want to sort of look at the structural model here, they quote the example here as using half adder. I got half adder stored in the database already. Half adder, remember just now I talked about only 2 input, A and B. All right, so now instead of use A and B, they use I1, I2 as the inputs, and the output is carry and S. So I have, okay, this half adder in my database already. I also have my OR gate that I generate on my own. So this OR gate, okay, that I generate on my own here, okay, actually is the same as the OR function, but I purposely generate this OR gate to show you the structural model. Then with this, okay, I use some wire, 3 of them. I try to connect up this circuit here and make them form a full adder. Okay, make them form a full adder. How they do it? So before, okay, they want to sort of interconnect this component at time, they must call out this component. So half adder, you call it out one time, but you can use it for many times. So you call out once only, and you can use more than one time. Same thing happens to your OR gates here. All right. Every single wire that you are using here, you must declare under your signal. Okay, so we look at the example of the structural model. So these parts here begin 1 half adder, 2 half adder, 1 OR gate. Because you have 2 different half adder, 2 unit of a half adder here, so you label another new name for it. This the first half adder, I'm going to call it as a HA1. Second one, call it as a HA2. This one, although only one, I still use OR1 because OR is a OR gate OR. So you cannot simply use to make it different OR1. All right. So now let's see, okay, the structure for this, okay, based on, okay, the interconnections of these parts here. So you find that, okay, I have HA1. Now I call it HA1. What is this HA1 here? Actually, from the components of your HA. What is a HA1 here? Actually, from the component called your half adder. So instantiate, okay, half adder. I repeat, what is a HA1 here? All actually come from half adder. My half adder here having, okay, different input. So A input, B input. Same thing here. A input, B input. Then they got 2 output. One is the, I use a carry, okay. Wait, let's look at here, okay. Component. Oh, I make a mistake. So here it's called I1, I2. Sorry, I make a mistake. I1, I2 carry and S. Yeah. So I based on, okay, this one here, I know, okay, my this HA1 here, got an input called I1, got an input called I2. Same thing apply to this because they are using the same half adder and they have an output C, okay, C and an output called S. My C is a carry, because too long, okay, carry, so this is a S. So this is my half adder that I know, okay, from these components here. Now, based on the connections here, they tell me that, oh, I1 is connected to A. My I2 is connected to B. Okay, this is the one. This is the one. Carry is connected to S1. What is S1? Actually, is your signal, isn't it? So that's why I say I differentiate it this way. This is a signal, a wire. Next, my S is connected to another wire called X2. Okay, I finished the connection for my first half adder. Then the second half adder now, where does the I1 being connected to? Connect to your X2. So it's a wire. Whole thing is a wire. So I mean, it's quite clear that, okay, you want to connect these two, you need a wire, isn't it? In the hardware, you know, take a wire, connect to them. Then the I2, I connect it to a carry in. This one, okay. Then this C carry here, I connect it to another wire called X3. And lastly, the S here connect to a S. So done for my half adder 2. Next, my OR gate now. Okay, so make it smaller. Okay, my OR gate now. So you find that okay. Now my OR gate now here tells me that, okay, my OR gate in this part here, the OR gate. So maybe I draw my OR gate here, OR gate. OR gate got 2 input, I1 input here, I1 input, I2 input, and 0 is the output. Okay, so I know this one already. Then now my I1 is connected to X1. I1 is connected to X1. Of course, this one must be a wire. Okay. And I2 connected to X3 is also a wire. Lastly, the O is connected to C out. I draw too big already, okay? My C out is here. Okay, and now if I were to sort of so you find that, okay, in a structural model, they specifically tell you the connections of the component that you are using or the entity that you are using by indicating the which point go to connect to which point or which port connected to which port. So this is the structural model. All right. Of course, some students can argue that, okay, I don't want to generate all one, can or cannot. Answer is can. But this one here is an example to show you. You can generate your own gate if you want to. But of course, you are making your life here more miserable. All right. So your S output is here. All right. So this is our structural model. Okay. With this, okay, now you are going to find that I want to finish this one here first. In my structural model just now, I got half adder 1, half adder 2, and the OR gate. How does a half adder, okay, are being generated? Maybe using some gates. Okay, so you use some gate, you generate, form a simple entity. With another 2 simple entity, you join them together to form your half adder. So this part here, trying to tell you here, you can do hierarchical design. Slightly tougher circuit, you can break them into smaller parts. Okay, you can break them into smaller parts. You design from an easy one first, combine them. Confirm this one here is working, then come to here, no error. Come up to here, also no error. That's what we want. Okay, so difficult design, don't always start from here. Always start from very simple bottom. All right, okay, so you are going to find out, okay, my design, if it's more complex one, I can actually have a lower level, okay, lower level behavioral, lower level usually behavioral. Slightly more complex, you join these two, join them together. So this one here, structural. Join these two together, structural. Another behavioral, join all these three together forms your structural model. All right, so this particular entity here is the the top level, so-called the top level. Then you find that this top level here can contain, okay, a structural model as well as behavioral model for the whole design. So single entity can contain multiple, okay, multiple design structure. Okay, so this is what is being mentioned here. Okay. Like I already show, okay, how to get this part here from this entity. All right, so you can have one to many. So instead of just you can, okay, I can make use of this one here as a structurer. Go and describe the connections of your gate instead of making use of the data flow this way. But of course, okay, when come to this full adder here, this is easier compared to this one. If I didn't work out based on this part here, I just work out this, okay? How I work out this actually come from the basic circuit design. So when I cover the full adder that time, okay, you'll come and you can actually prove that, okay, these equations here are correct. Okay, so for this part here, I stop now and we go for lunch. So we come back 1 hour later. So any questions before we end this part here? Stop. Am I covered too much? How do we, okay, justify delay time? This one here, if you really want to model, you have to study the data sheet law. Q bar, if you don't use it, okay, in VHDL, you no need to design, no need to assign also can if you don't use it. Okay, if you don't use it, no need to declare also can. Any question that I missed out, okay, that I never answer? What are the symbol? What do you mean by what are the symbol in this case? Well, symbol is like macam ini lah. Okay, so if it's a circuit, normally, okay, it looks this way. But of course, okay, this one cannot use in a VHDL. So normally, okay, we will label it as Q bar, Q bar. Underscore, Q underscore bar. Okay. Basically, structural and behavioral will use same result. If you do it correctly, yes, Goving. But we normally go for easier one. Depending on which one is easier, okay, we go for it. Design ma. All right. Always try to go for easier design. Why does a clock event? What does clock event mean? Clock event in this case because okay, it is a very short duration. Things happens okay in a very short durations. So in reality, okay, because your clock moves so fast, so time. Let's say for time this is one. I use the word second just for explanation. This one also 1 second.
So 1 second you are at 0. Same thing at 1 second also you are at 1. Okay, logic 1. So this is logic 0. This is a logic 1. So therefore this one here it is called as event in VHDL. Very short durations and or no time difference. Okay, things happens. Okay, so this is the part we call it as event. If event, okay, clock event, clock event and clock 1, okay, then this one here refer to this rising age, okay. But terbalik, let's say clock event, you elevate clock equals to logic 0, then you are talking about falling age. So this part end at 0. This part end at 1. So this is a 1. Okay, Song Jian, am I answer your question? For the DFF, if reset pulse is active low, then no need to work already. Like go from falling age and stay the same. Then flip flop will work only once. Yes, you are right, because reset not changing So process say no need to work. Process is sensitive to whatever variable inside the bracket. If those variable inside the bracket remain unchanged, then process no need to work. Means that those programs inside the process not going to being generated. Going answer your question? It's the same as what we are having for our hardware. So imagine you are not just purely writing software, you have to now trying to relate it to the actual components. My actual component is every time clock comes, you must work. Every time reset comes, you must check whether what is the output. If clock spoil already, never change, your reset never change, then you don't work because spoil already You don't work in a normal way anymore. All right.
Okay. So is counting pulse 5 pulses work 5 times? Yes, you are right. Clock comes 5 times, I work 5 times. Clock come faster, I work faster. Harder I need to work harder. Okay. Any more questions? I'm sure some of you very hungry already. If no, then we stop here. We come back 1 hour later. Ayo, breakfast also not yet Kok Wing, what happened to you? Poor thing. Okay. Go and eat before you come for class Aiya. Like me, if I don't eat, I cannot talk. Okay, anyway, we stop here. So we come back at 1 hour later, means in this case here, 1:13. I need to go and prepare my lunch already. Okay, see you later.